Welcome to today's paper reading. Today's paper is titled, Fast Inference of Mixture of Experts Language Models with Offloading. This paper was published on the AR14 preprint by Artyom Eliseev and Denis Mazur from Moscow Institute of Physics and Technology. The abstract discusses the challenges and strategies associated with running large language models, LLMs, efficiently. With the increasing adoption of these models, practitioners are exploring methods like the use of sparse mixture of experts, MoE, architectures. MoE models activate only a fraction of their layers for any given input, enabling faster token generation compared to dense models. However, this comes at the cost of increased model size, making them resource-intensive. This work addresses the problem of running large MoE language models on consumer hardware with limited resources. It introduces a novel parameter offloading strategy that leverages the inherent properties of MoE LLMs to accelerate offloading. This strategy allows the execution of models like Mixtral 8x7b with mixed quantization on standard desktop hardware, and even free-tier Google Colab instances. The introduction of this paper highlights the significant advancements in natural language processing driven by large pre-trained language models such as GPT-3, GPT-4, Palm, and Gemini. However, the deployment of these models, especially open-access ones like Llama and Falcon, faces challenges due to their high computational demands. Techniques like model compression and parameter offloading are necessary to make these models usable on more affordable hardware. Additionally, the paper discusses the mixture of experts, MoE, architecture, which introduces sparsity to improve compute efficiency. Despite their advantages, existing techniques for efficient inference are not optimized for MoE-based models, leading to suboptimal performance. The concept of mixture of experts, MoE, language models builds on the idea of training ensembles of specialized models, known as experts, and a gating function to select the appropriate expert for a given task. This approach involves simultaneously training the gating function to choose the best experts and training the experts themselves on samples assigned by the gating function. Shazir et al., 2017, developed a sparsely gated MoE language model, which includes a recurrent neural network backbone and an MoE module with up to 131,072 experts. The model selects for most suitable experts for processing each token based on the latest hidden state. This MoE model not only improves perplexity, but also learns interpretable expert specializations. Recent work has explored MoE with transformer-based language models for various applications, demonstrating that MoE models are cheaper to train and infer but require more parameters than dense models with equivalent perplexity. The methodology in this work focuses on optimizing the inference of modern mixture of experts, MoE, large language models, LLMs, on desktop and low-end cloud instances. The generative inference process is divided into two main phases, encoding the input prompt and generating tokens based on that prompt. The encoding phase is parallelized layer by layer, while the token generation phase is sequential, both token by token and layer by layer. This sequential nature limits inference speed due to the need for frequent parameter fetching from system memory. To address this, the authors explore patterns in how the MoE model loads its experts and propose methods to exploit these patterns for faster inference. One such method is LRU caching, which keeps active experts in GPU memory to reduce loading times. Another method is speculative expert loading, where the system guesses the next experts to load, potentially reducing latency if the guess is accurate. These techniques aim to enhance the efficiency of MoE model inference on resource-constrained hardware. Figure 1 illustrates the expert loading pattern in Mixtral 8x7b instruct for select layers. The blue cells signify that a particular expert was active when encoding a specific token, with deeper blue indicating a higher gating weight. Additionally, small gray squares depict which experts are cached using an LRU cache for k equals 2. In this section, we evaluate the effectiveness of expert offloading strategies such as LRU caching and speculative loading. We measure the expert recall, which is the fraction of times an expert needed for inference is already available on the GPU. We also test different quantization schemes including FP16, 4-bit, 3-bit, and 2-bit on the Mixtral 8x7b model, measuring performance in terms of Wikitext2, C4, and MMLU scores. Finally, we assess the inference latency across various hardware setups, focusing on the number of tokens generated per second using offloading techniques. Table 1 presents the evaluation of perplexity and model size for the Mixtral 8x7b model under various quantization schemes applied to shared attention and experts layers. The table highlights the trade-offs between model size and perplexity metrics such as Wikitext2, Wiki2, and C4 perplexity, as well as 5-shot MMLU accuracy. It also includes a comparison with a Mistral 7b 4-bit quantized model, which serves as a benchmark. The green values indicate the chosen configurations for full system evaluation, reflecting optimal performance size trade-offs within the target hardware constraints. Figure 2 illustrates the performance of LRU caching and speculative loading strategies in modern mixture of experts (MoE) models. On the left, the graph shows the LRU cache hit ratio for various cache sizes, K, indicating how often the required experts are already available in the cache. On the right, the graph displays the recall of speculative loading when preloading a different number of experts, with regular lines representing loading 1 layer ahead, dashed lines for 2 layers ahead, and dotted lines for 10 layers ahead. This figure helps in understanding the effectiveness of these strategies in reducing inference latency. Table 2 presents the inference speed of the Mixtral 8x7b model on low-tier hardware, specifically measured in tokens per second. The evaluation includes 4 hardware setups: a free-tier collab instance with a T4 GPU, a gaming laptop with RTX 3080 mobile, a mid-range gaming desktop with RTX 3060, and a high-end data center server with a 100-80 GB SXM. The results indicate that all configurations can generate between 2 to 4 tokens per second using the full algorithm. Notably, the RTX 3060 desktop performs nearly as well as the higher-end RTX 3080 mobile, likely due to shared bottlenecks in PCIe architecture. This table highlights the performance trade-offs and efficiencies achievable with different hardware setups for Mixtral 8x7b inference. In this study, the authors explored methods to accelerate mixture of experts, MoE-based language models on consumer hardware with limited GPU memory. They introduced a MoE-centric approach to offloading and examined the impact of mixed quantization on perplexity and performance in language understanding tasks. The evaluation demonstrated a significant increase in generation speed compared to naive approaches, even on consumer-grade hardware like free-tier Google Colab. This method offers a practical solution for inferencing large MoE models on resource-constrained hardware, facilitating broader access for research and development. For future work, the authors plan to investigate additional offloading strategies, particularly those based on speculative expert prediction. They also acknowledge MoBiCamat for valuable discussions on mixtral quantization. Thank you for watching.